Okay, so today we're going to solve equations that contain fractions. If you take a look at this whole page, all fractions in those equations. But that's okay. We can still solve for the value of x in each of these. And the first type we're going to solve is called the cross-multiplying type. Cross-multiplying is a process you use to solve for the missing piece in a proportion. Remember, a proportion is just two fractions set equal to each other, like this. And if one of those four pieces is missing, you can cross-multiply to solve for it. Well, if you take a look at exercise 1A, on the left side we have ourselves a fraction. I mean, the top of it, the numerator is kind of a mess, but it is a numerator over a denominator, so it is a fraction. And on the right side of the equation we have a 9, but we know that we can put 9 over 1, and it's equivalent to 9. Now we have a fraction set equal to a fraction. So this is actually a proportion. We can cross-multiply to solve it. We go diagonally this way. 1 times 6 parenthesis x plus 2 just gives us 6 parenthesis x plus 2. Multiplying by 1 doesn't change anything. The equals goes in the middle. And now we're going to multiply this way. 4 times 9 gives you 36. Look, our fractions are gone. And we know how to solve this. To get rid of the parentheses, we distribute. 6 times x gives me 6x. 6 times 2 gives me 12 equals 36. To get that x by itself, I'm going to subtract 12 from both sides. And with 6x equals 36 minus 12 is 24. Dividing by 6 on both sides, I end up with x equals 4. 24 divided by 6 is 4. Now, as we talked about previously in set notation, here's what that would look like. X such that x is equal to 4. In letter B, same situation. We have a fraction on the left side. This time the top and the bottom is an expression, but it's still a fraction. And on the right side we have a 2, which we can put over 1 to turn into a fraction. We now have a proportion. We can cross-multiply to solve this. Now, when I do 1 times 3x plus 5, technically I could write it this way. 1 times 3x plus 5. The equals goes in the middle. And then when I do 2 times 2x minus 1, it's going to look like this. Now, typically when you multiply 1 times 3x plus 5, you would just write 3x plus 5 because distributing a 1 through the parentheses doesn't change anything. The reason I wrote it this way for you today is because I just want you to see the difference between when you're multiplying by 1 and when you're multiplying by a number greater than 1, like 2. It really does have to get distributed through the parentheses. On this side, we're left with 3x plus 5. On this side, you're going to get 2 times 2x, which is 4x, and 2 times negative 1, which is negative 2. This one's a little different than letter A because now we have a variable on both sides. We have to get the variable to one side, so I'm going to subtract 3x from both sides. I certainly could have subtracted 4x from both sides as well, but I like to keep my x variable positive. These cancel. I'm left with 5 is equal to 1x minus 2. 1x comes from taking 4x and subtracting 3x from it. Adding 2 to both sides, you see that x is equal to 7. On this next one, you have a fraction on the left side and this expression on the right side. Well, still, even though that's an expression, you can put the whole thing over 1. Make it look like a fraction, and now we can cross-multiply to solve it. 2x times 1 gives me 2x. The equals goes in the middle. And then we're going to do 3 times 14 minus 4x. When we distribute to get rid of the parentheses, 3 times 14 is 42. 3 times negative 4x is negative 12x. Again, we have the variable on both sides. Your goal is to get the variable on one side and a number on the other side. Well, since we already have the number on the right side, I'm going to get rid of the 12x. Add 12x to both sides. 2x plus 12x gives me 14x. These cancel. I'm left with 14x equals 42. Dividing both sides by 14, 42 divided by 14 is 3. X is equal to 3. Now when we take a look at these next examples, you're going to see a little difference here. Let's say that the x over 5 and the plus sign were not there, that this piece here were gone. If you covered that up with your finger, you would just see that it was x over 2 equals 14. You could put the 14 over 1 and cross multiply to solve it. You actually cannot cross multiply to solve this one yet, because it's not a fraction set equal to a fraction, it's a sum of two fractions set equal to a fraction. So in order to cross multiply, we have to first find the sum of x over 5 and x over 2. Now back in Ms. Dromgold's class, when you learned how to add fractions, you learned that you need a common denominator. Our denominators are 5 and 2. So I'm going to use 10 as my common denominator, because 5 is a factor of 10 and 2 is a factor of 10. Well, if we change the denominator to 10, the numerator has to change as well for the fraction to remain equivalent. Well, 5 times 2 gave me 10, so I just need to multiply the numerator by 2 as well, giving me 2x. And 2 times 5 gives me 10, so I just have to multiply the numerator by 5 as well, and it gives me 5x. And now I can add these fractions together. 2x over 10 plus 5x over 10 gives me 7x's over 10. I can set that equal to 14 over 1. And now that we've added those fractions, we have a fraction set equal to a fraction. We can cross multiply to solve it. 7x times 1 gives me 7x. The equals goes in the middle. And 10 times 14 gives me 140. I end up with 7x equals 140. To finish getting x by itself, I divide both sides by 7, and 140 divided by 7 is 20. You get x equals 20. In set notation, again, x such that x equals 20. You will never get points off if you don't write your answer in set notation. I just want you to be familiar with it in case on a multiple choice question the state decides to write their answers in set notation. Or in case the directions ever simply say write your answer in set notation. It could happen. On this next one again, we've got to actually add these fractions together before we can cross multiply. Hold on one second, I got to let Murphy in. Alright, so again, this next one we have to add these fractions first. Our denominators are 2 and 6. I'm going to use 6 as my common denominator, because 2 goes into 6 and so does 6. 2 goes into 6 3 times. Multiplying the numerator by 3, I get 3x here. We didn't change the denominator here, so the numerator doesn't change either. 3x over 6 plus 1x over 6 gives me 4x over 6. I can put the 2 over 1. I now have a fraction set equal to a fraction, so I can cross multiply. 4x times 1 is 4x. The equals goes in the middle. 6 times 2 is 12. Dividing both sides by 4. 12 divided by 4, you see x equals 3. Now this next one, again, it looks like you can use 6 as your common denominator, because 3 goes into 6, and obviously so does 6. 3 goes into 6 2 times. Multiplying the numerator by 2, 2 times 2x gives me 4x. 2x over 3 is equivalent to 4x over 6. This one doesn't change. 4x over 6 plus 1x over 6 is 5x over 6. I can put the 5 over 1, and now I can cross multiply. Oh, I wish I could videotape my dog right now. For some reason, he doesn't realize that that tail is attached. Cross multiplying 5x times 1 gives us 5x. The equals goes in the middle. 6 times 5 gives you 30. Dividing both sides by 5, you see that x is equal to 6 because 30 divided by 5 is 6. So that's when you have a sum set equal to a number. Before you can cross multiply, you have to add the fractions together. It could also happen with a difference. You would have to subtract the fractions, but you'd use the same process. Excuse me. You might be wondering why I rewrote the same 3 equations again. I did that because I'm going to teach you a second method where when you have a sum or a difference set equal to a number. And this is what the math teachers at Odyssey call the I hate fractions method. If you like this method better than the common denominator method, then go ahead and use it. Doesn't matter to me which one you use as long as you know what you're doing and you get the right answer. Here's how you use the I hate fractions method. You basically take a look at the two denominators you want to get rid of. In this first one, we want to get rid of a 5 and a 2. So what you do is you take the denominators you're trying to get rid of and you multiply each term in the equation by that 5 and that 2. Even this guy out here. You got to do every single term in the equation because otherwise you won't keep the equation balanced or equivalent to the original equation. Now look what happens when we do that. In this first term, we have a 5 in the top and a 5 in the bottom. Guess what? Those cancel out. You're left with just 2 times x, which is 2x. In this second term, this 2 in the bottom cancels with this 2 in the top. You're left with 5 times x, or just plus 5x. On this side, you have nothing to cancel with in the bottom because this 14 is just over 1. So you just multiply 14 times 5 times 2. Well, 5 times 2 is 10. 10 times 14 is 140. See? You hated fractions, so you got rid of them. Now we can combine like terms. We end up with 7x equals 140 because 2x plus 5x is 7x. Dividing by 7 on both sides, 140 divided by 7 is 20. And 20 is the same thing we got up here. We got x equals 20. Just used a different method of solving. In this next one, the fractions we want to get rid of, or excuse me, the denominators we want to get rid of are 2 and 6. So I'm going to multiply this term by 2 and by 6. This term by 2 and by 6. And even this term over here by 2 and by 6. Now this 2 in the bottom cancels with this 2 in the top. I'm left with 6 times x, which is just 6x. This 6 in the bottom cancels with this 6 in the top. I'm left with 2 times x, or just 2x. And on this side I have 2 times 2, which is 4, times 6, which is 24. Combining like terms, 6x plus 2x is 8x. I end up with 8x equals 24. Dividing both sides by 8, you get x equals 3. On this last one, I apologize there's not a lot of room, but the denominators we want to get rid of are 3 and 6. So I'm going to multiply this term by 3 and by 6. I'm going to multiply this middle term by 3 and by 6. And even the 5 gets multiplied by 3 and by 6. 3 in the bottom cancels with the 3 in the top. I'm left with 6 times 2x, which is 12x. 6 in the bottom cancels with the 6 in the top. I'm left with 3 times x, which is just 3x. 5 times 3 is 15. 15 times 6 is 90. I'm left with 12x plus 3x equals 90. Combining my like terms, 12x plus 3x is 15x. I get 15x equals 90. Dividing both sides by 15, I get x equals 6. 90 divided by 15 is 6. Same thing we got up top, we just used the I hate fractions method instead of the common denominator method. So when you come into class next time, be ready to work with these equations involving fractions and have your notes ready to show me, and have a wonderful night. Okay, so today we're going to talk about a concept called literal equations. We've been solving equations so far in Unit 2 where there's a number as an answer. Or maybe there's no answer, or maybe there's an infinite number of numbers that are solutions. With literal equations, hold on one second. With literal equations, there's actually no number as your solution. You end up with an expression that's the solution to the equation. So here in exercise 1, we're going to solve each of these equations for the value of x, which, as you know, means get x by itself. So first we'll solve one that is not a literal equation, but an equation where there will be one number as your answer. 5x plus 3 equals 33. You can see there's only one variable in there to solve for. It's x. And it's pretty simple to solve for it. To get x by itself, we would subtract 3 from both sides. That gives you 5x equals 33 minus 3 is 30. To finish, divide both sides by 5. And you see that the value of x that makes the equation true is 6. This next example is what we call a literal equation. Instead of 5x plus 3 equals 33, we have ax plus b equals c. It still has an x in there that we can solve for, but we certainly won't be able to come up with an answer like x equals 6 because we don't know what a, b, and c are. But we are going to use the exact same method to get x by itself. Over here, we had plus 3, so we subtracted 3 from both sides. Over here, we have plus b, so we're going to subtract b from both sides. The b's cancel. You're left with a times x is equal to, well, we can't come up with one value for c minus b like we did over here. 33 minus 3 was 30. All we can do is write the expression c minus b. Now, over here, we had 5x equals 30, so we divided both sides by 5 to get our answer. We're going to do the same thing here. We have x times a. We're going to divide both sides by a to get our answer. You're left with x equals c minus b over a. And that's your answer. Notice the answer is not a number. The answer is actually an expression. All right, let's take a look at a couple more examples. You'll see the two examples in exercise 2 look pretty much the same in terms of format, but this one will come up with a numerical answer. This one is a literal equation. Remember, a literal equation is an equation where there's more than one variable, and you're just asked to solve for one of those variables. So let's solve the numerical equation first, because that we're good at. We have to get this fraction that contains the x by itself, so to do that we're going to add 7 to both sides. So we end up with x plus 5 over 2 is equal to 3 plus 7 is 10. Now putting the 10 over a 1, we can cross multiply to solve this proportion. 1 times x plus 5 is x plus 5. The equals goes in the middle, and 2 times 10 is 20. Subtracting 5 from both sides, we end up with an x value of 20 minus 5, or 15. On this side, we're going to use the exact same steps, but again, we're going to end up with an expression as our answer instead of a number like 15. Going to get this fraction by itself by adding c to both sides. We end up with x plus a over b is equal to, again, when we do, oh, look, I made a mistake. Let me back up. That should have said plus c. to both sides. We end up on this side with not a number, but with an expression d plus c, which I can still put over 1 and cross multiply to solve. 1 times x plus a is x plus a. The equals goes in the middle. And b times d plus c will look like this. b times d plus c. So we almost have the x by itself here, just like we almost had x by itself here. To get x finally by itself, we subtracted 5 from both sides. So to get x finally by itself over here, we're going to subtract a from both sides. You end up with an x equal to a b times a d plus c minus an a. There's your expression. It's also your solution to this literal equation. All right, number 3 is a multiple choice question. And I put this on here purposely because I like for kids to think about multiple choice questions when they see them on the Regents exam as non-multiple choice questions. I want you to pretend that these answers aren't here, because if you look at the answers first, a lot of times these answers are written very systematically. The person that wrote this problem knows the common mistakes you're going to make. So sometimes looking at the answers first is not a good idea because some of those distractor answers lead you in the wrong direction. So let's just pretend those aren't there. And we'll rewrite this equation over here. And we're being asked to solve for x in terms of h and k. We've heard that before. We've talked about how find the area of the circle in terms of pi means that you're going to have the pi symbol in your answer. Well, solving for x in terms of h and k means that your expression, that is the solution to this literal equation, is going to have an h and a k in it. So here's the variable we're trying to get by itself. Keep in mind also that you could be asked to solve for k in terms of h and x. You just got to read the directions. Hold on, I got to let the dog out. Okay, Murphy was under my bed, eating the lining from the box spring. I just went to take him outside. He's not going outside, so I closed my door. He'll probably start barking. We'll just have to ignore him. All right, so the first thing to get x by itself here is let's get rid of this plus k by doing minus k to both sides. We're just going to take step by step and try and get that x all by itself. On this side, we end up with 2 times x minus h equals 8 minus k. Well, the next thing we need to do is try and get at least this parentheses containing the x by itself. And it's multiplied by 2. So the opposite of multiplying by 2 is dividing by 2. You end up with just, since these 2's cancel, x minus h equals 8 minus k over 2. So we're almost there. X is almost by itself. It still has a minus h stuck to it, so we're going to add h to both sides. These h's cancel. You're left with x equals, you've got 8 minus k over 2 plus h. Now, if you take a look at our answer choices, I don't see this up there as an answer, which means that the person that wrote this problem must have simplified our solution a little bit further. So let's see what we can do to simplify this a little bit further, and hopefully our simplified version of the answer will show up as an answer choice. Remember, dividing 8 minus k by 2, that's the same as doing this. 8 divided by 2 minus k divided by 2 plus h. Well, 8 divided by 2 is 4. So do we have an expression up there that says 4 minus k divided by 2 plus h? We do, right here. It's written in a little bit of the different order, but the 4 is still positive, the h is positive, and the k over 2 is negative. And the commutative property for addition allows us to switch the order, so that is equivalent to the answer that we got. Now we're going to look at a couple examples where we have to get the variable to one side. Again, we'd like to solve this equation for x. And let's start with the situation where we know the values of a, b, c, and d. Okay, here you've got an 8x on the left side, a 5x on the right side. So I'm going to get the variable to one side by subtracting 5x from both sides. 8x minus 5x is 3x, plus 1 equals the 5x minus 5x cancel. You're left with 22 over here. To continue getting x by itself, we subtract 1 from both sides. You get 3x equals 21. Finally, dividing both sides by 3 gives you a solution of x equals 7. Now we're going to solve the exact same equation, but we're replacing the 8 with an a, the 1 with a b, the 5 with a c, and the 22 with a d. But we're going to solve it the exact same way. We'll start by subtracting ax to both sides, like we did in the first equation. So you're left with b is equal to cx plus d minus ax. Well, now we've got 3 terms on this side. Only 2 of them have an x in it. And that's okay, but let's get rid of any terms on this side that don't have an x in it, like the plus d. To get rid of plus d, we're going to subtract d from both sides. So we get b minus d equals cx minus ax. I've seen that they like to put this type of literal equation on the Regents exam a lot because it practices a skill that we haven't even gotten to yet called factoring. So this is really cool that we're going to talk about it now because it'll give you a little heads up as to what you're going to be doing a lot of later in the year. When you're solving a literal equation, if you get down to having the x on one side only, but instead of it being in one term like it was here, it ends up in 2 terms like it is here, think about how you're going to get the x by itself. You can't divide this piece by c and this piece by a. Can't do that. We have to somehow figure out how to isolate the x. Well, we've done a lot of distributing. To isolate this x, we're going to do a process called undistributing. You'll notice that there is an x in both of these terms. So what if we were to pull that x out of both of those terms and undistribute? What expression would have had to be in here if when we distributed the x, we ended up with cx minus ax? Well, it would have to be c minus a. Let's just check and make sure this is right. Is x times c equal to cx? Yeah, it is. Is x times negative a equal to negative ax? Yes, it is. And by undistributing, which another word for that is factoring, what we've done is we've isolated this x all by itself here. It's multiplied by c minus a, but we know how to unmultiply by c minus a. We divide both sides by c minus a. These cancel. You're left with x is equal to b minus d over c minus a. Let's see if we can do another one where this is the case, where we have to do some undistributing to get the x by itself. We're going to solve for x in terms of a, k, and h. Let's come down here and rewrite this. Ax minus k equals 3 times the sum of x and h. Well, we've already learned that we distribute to get rid of parentheses, so even in a literal equation, we could do that. we end up with ax minus k equals 3 times x is 3x, 3 times h is 3h. Well, we got variables on both sides. Let's get the variable on one side. I'm going to do minus 3x here and minus 3x over here. So now I have ax minus 3x. Oops. I have a minus k over here equals just 3h over here. You can tell already that you're probably going to have to do the undistributing because you see an x in both terms, but before you do that, you have to make sure those are the only terms on this side. So let's get rid of the minus k by adding k to both sides. So now we have ax minus 3x equals 3h plus k. So now again, we're stuck in the same situations. Not a big deal, but instead of having the x in one term, we have the x in two terms. So the only way you can isolate that x is to factor it out or undistribute. Let's pull the x outside the parentheses and think about what would be left in the parentheses. Well, if when we distributed the x, we got ax minus 3x, that must mean there was an a minus 3 in here. Sure enough, x times a gives you ax. X times negative 3 gives you negative 3x. We just undistributed to get that x by itself. Now that x is multiplied by the quantity a minus 3, we just have to unmultiply by a minus 3 or divide by a minus 3. You're left with x is equal to 3h plus k over a minus 3. Look at your answer choices. It looks like it's choice A. So hopefully you guys got all these notes down. I've modeled for you how I want you to take notes. This is what I need you to do. Probably took us about 12 to 15 minutes. I'm not really sure. But we're done, and now we're going to practice this skill.